This video is about the graphical method for solving linear systems in two variables. For our notes, we'll just identify a couple key steps, and that is, first, we're going to have to graph each equation. And so we'll do that just the usual way of graphing. There'll be lines, linear systems here, so these are just graphing lines. And then secondly, we're going to have to search for any intersection points, if they exist, and the x and y coordinates of any such intersection point would be the solution. Now there's some important vocabulary that accompanies this process. And so let's understand this. A system with no solution is called inconsistent. We've seen that already. This occurs when variables drop out in the process of solving, leaving numeric equations that is not true. That's what we've already been seeing when solving algebraically. But now, when we're doing things graphically, we'll say this occurs when a system has two distinct equations whose graphs are parallel lines. If, as we discussed in our notes above, if the intersection point is where the solution lies, but parallel lines do not intersect, then of course there would be no solution for that. Okay, secondly, we've already discussed that a system with infinitely many solutions is called dependent, and algebraically we see that happen when the variables drop out and what we're left with is true. But now, graphically, this occurs when a system has two equations whose graphs turn out to be the same line. So this may not be obvious as you take a first glance at the way the equations are given, but sometimes just adjusting them to get them into slope-intercept form or something like that to graph, you can spot it that indeed both equations are actually the same line. So if that occurs, then we'll call this a dependent system, and of course we'll write our answer accordingly. Let's consider an example where we want to find all solutions of the system graphically, and we want to verify our result with a graphing calculator. So let's go ahead and take a look at our first system here. The first equation in it is 2x plus 6y equals 0. The second equation is negative 3x minus 9y equals 18. All right, for this system, notice we'll have to graph both of these equations. We'll use a couple different colors to do that. The first equation I'm going to do in orange. Remember, that was the 2x plus 6y equals 0. So I'm going to grab that equation and just bring it over somewhere where we can work on it as needed to be able to graph it. The second equation I'll do in kind of a brownish red color. That one was the negative 3x minus 9y equals 18. We can use any valid graphing method to graph these. That might include getting it into slope-intercept form, or it might include finding the intercepts. Given the way these are set up, I'm going to probably choose that we want to find intercepts in these. I just think the numbers are set up nicely. Okay, I'll explain what that means in a second here, but let's first kind of dive in. I want to find intercepts, and an easy way to organize that is just to make an xy table and then plug in some zeros for x and y. Now, in this orange equation, the first one, which was 2x plus 6y equals 0, if I let x be 0, that first term would just disappear, which means I would have just 6y equals 0, but then that would mean y is 0 as well if I solve for that. Now when y is 0, you'll notice we already encountered that point. It turns out that the origin is both the x and the y intercept. Now that's fine, but that means it actually isn't enough to be able to graph a line, right? We need at least 2 points. So that means we're going to have to try to put this equation into slope-intercept form in order to graph it. So I'll just go ahead and solve for y. If I subtract 2x from both sides, that would give us 6y equals negative 2x. And then if we divide by 6 on both sides, we'll have y equals negative 1/3 x. Okay, so that would be reducing the 2/6 fraction to be negative 1/3 there. Okay, so there's our slope-intercept form. Now we already decided or found that the origin is the y-intercept. If my slope is negative 1/3, then I could either go up 1 left 3 or down 1 right 3, and that's just kind of using the rise and run. So I'll go down 1 right 3 points, or I could go up 1 left 1. Okay, really only 2 points is necessary, but 3 just helps make a better looking graph. I want to connect all 3 of these points to form a line, and that will be the line of our first equation shown here in orange. For our second equation, let's try the same trick to see if we can get away with just using the intercepts. If I use a table and put in some zeros for x and y, when x is 0, the first term's gone, I'll have negative 9, y equals 18. That means y is negative 2. So that's fair enough. 0, negative 2 is an intercept. I can plot that point. When y is 0, the second term drops out, giving us just negative 3x equals 18. In that case, x would be negative 6. So the point negative 6 comma 0 would be my x-intercept. If we go ahead and plot these 2 points, or I'm sorry, plot this line connecting those 2 points, we may start to get a little suspicious here. Now, here's the deal with graphing. Okay, graphing by hand is usually not a fantastic way to solve systems because by hand, our drawings aren't perfect and there could be some error, and so it's not an excellent way to use a picture to find things. But this is a great example of it. You'll look at these 2 lines and go, those seem kind of parallel. Like maybe they are parallel, but it isn't completely clear yet if they are. So one way to verify whether they are parallel would be to put the second line also in slope-intercept form and see if that yields the same slope. So let me drag this line down here. But to solve for y, really I'll be adding 3x to both sides. That means I could have negative 9y equals 3x plus 18. If I then divide everything by negative 9, my equation will be y equals negative 1/3, that's dividing by negative 9 and reducing, minus 2, going all the way across. Well, sure enough, you'll notice the slopes of both of our lines seem to be negative 1/3 when compared in slope-intercept form, which means these are parallel lines, which means there actually is no solution because, of course, these lines never intersect. And the intersection place is the solution for a system when solved graphically. Okay, so parallel lines, which we could just say is also known as inconsistent. To use some of the vocabulary we discussed earlier, but there is no solution due to them being parallel. Now, the second part of this problem said to verify the result in a graphing calculator. But unfortunately, it's just not very exciting to verify parallel lines on the graphing calculator. We already know they're parallel because of the same slopes that we identified. So I'm going to demonstrate the power of the graphing calculator, but I'm just going to change the equations to demonstrate it. Okay, so this is really not this example, but it still will show you a very powerful tool on this calculator. So the new equations I'm creating, you can see I've typed in here on the screen. The first one is y equals negative 1/3 x. Now that was one of our equations in this previous problem. But I changed the second equation to be something not parallel with it. I just picked 7x minus 10. So we're going to start by taking a look at these 2 lines. We'll try a zoom, and then remember zoom 6 or zoom 4 usually gives you a nice standard window. Let's try zoom 4. And sure enough, okay. So we can see our lines do intersect. It looks like it's somewhere in quadrant 4, but I purposely tried to pick some numbers that would create an intersection that's not nice. Like it looks like it's not, at some nice grid lines, if we had to estimate where that would be. And that's exactly the limitation of solving by graphing. If you're doing this by hand, there's really no chance that you'll get a really accurate estimate of where that intersection point is. So it's not a really good method in that way. But computer systems and calculators can do a fairly good job with it. So here's how. If you wanted to find out exactly where those intersect, or at least a pretty good approximation, what we'll do is go in and press second, and then our trace button, which takes us to a familiar menu, this calculate menu. We've used the value option and the 0 option, even the min and max before. Now we're going to go down to option 5, which says intersect. We're going to hit enter at that option. It's going to take us back to the picture of the graph, and notice there's a cursor that's sliding around on one of the equations. Now, there's a question in the bottom left corner that says first curve question. Okay, so the reason it's asking is because you could have, many different curves graphed on a screen at once. We only have two, so this shouldn't be too bad. But is that our first? Sure. It doesn't matter which one is the first or second. We'll hit enter. It'll then ask us for our second one. But notice the cursor hopped. If you can figure out where it is, and you can do so by using the coordinates at the bottom of the screen of the cursor, and then move the arrows right or left until, okay, there's the cursor. So notice now it's on the other line. Is that our second line? Yes. So we'll hit enter there. Now it wants a guess as to where they intersect. So we'll scroll back maybe a left notch or two until we get closer to the intersection. You probably won't hit it exactly, but that's good enough for a guess. So we'll hit enter, and it will spit out a pretty good approximation of where those lines intersect. So again, this is much better than graphing by hand, and truthfully, if anyone's actually solving a system by graphing in the real world, they're using some kind of computer or graphing system like this to get an approximation. And so we want to understand the concept done by hand, but then understand the technology's power to do it more accurately, which is exactly what I've just demonstrated with this different example. I gave you really a second example in this particular video that I made up because they're not parallel, and it's more interesting to see the intersect feature in that case. But it's a great feature. If you're doing it by hand, of course, numbers are typically, hopefully, nice enough to be able to see the concept done by hand. Otherwise, this would demonstrate solving something by graphing. You could get no solution, as we saw with parallel lines. You could get one solution, as we just saw in this example on the calculator. Or you could get infinitely many solutions if it turns out that you're graphing the exact same line, which actually shows up as only one line because you can't distinguish the two different lines if it's the same thing. But either way, that will give us the three different answer types possible for a system.